Today we'll be talking about the symmetry and transformations on functions for sections 2.4 and 2.5. Here are all of our listed out objectives for your reference. So starting off with symmetry, notice how all of the x values on the left-hand side of my axis and the x values on my right-hand side of the axis all have the same y values. So something like -3 and 3 both have the same y value, 4. When that happens, we say it's symmetric with respect to the y-axis. Essentially, if I can look at the graph and fold it along the y-axis here, and the two sides of the graph match up, that means that it is symmetric with respect to the y-axis, in the kind of natural idea. Well, we can do the same thing with the x-axis. So if I have a point where the x value is the same and the y values are opposite signs, then we say it's symmetric with respect to the x-axis. Notice this is not actually a function. It doesn't pass our vertical line test. But if I can fold it along the x-axis, if this were on a piece of paper, and the two sides would line up, then it's symmetric with respect to the x-axis. We can also have symmetry through the origin. So that's when my xy point matches up with a -x, -y point. We say that's symmetric through the origin. And if I rotate the graph by 180 degrees, so if I went all the way and rotated it twice, essentially, to have it completely upside down, the graph would look the exact same. That's how you tell when something's rotated, or reflected through the origin, or symmetric through the origin. So we don't have to always just use graphs to look at these things. We can actually test this with algebra. So to test if something is symmetric about the y-axis, you replace x with -x and see if you get the same function. To tell if it's symmetric with the x-axis, replace y with -y and see if it's the same function. And then to see if it's reflected through the origin, replace x with -x and y with -y and see if you get the same function. So let's see an example of that. We want to see if this function is symmetric with respect to the y-axis, the x-axis, and the origin. And you can see the graph on our bottom right part of the screen to kind of tell it, hopefully we get that it's symmetric with the y-axis. Because clearly this is symmetric with the y-axis here. So we want to test if it's symmetric with the y-axis. So you want to plug in -x for x. So doing that gives us -x squared, right? I got to plug in the whole thing in for x and square the whole thing, plus 2. Well, naturally, the square reduces the negative, right? Negative times negative goes away. So this is just x squared plus 2, which is, in fact, the same function we started with. So yes, it is symmetric through the y-axis. To look at the x-axis, well, we're going to look at -x squared plus 2. Stick a negative out front and see what happens. Then we get -x squared minus 2, and that is not equal to x squared plus 2, so it is not symmetric through the x-axis. This is what we call -y, essentially. -y is what we're looking at there. So now to tell if it's symmetric through the origin, we need to look at if the -x, so let's say y at -x, which is x squared plus 2, which we got in the first part, see if that equals -y, which was -x squared minus 2. Clearly, these two are not equal to each other, so it is not symmetric through the origin. It is only symmetric through the y-axis. Now we actually have names for these kinds of functions. So if a function is symmetric with respect to the y-axis, we say it's even. And essentially all you want to think about, well, does f of x equal f of negative x? So if I replace x with negative x, do I get the same thing? Then we say the graph of a function is, when it is symmetric with respect to the origin, we say that a graph is odd. So that is, for each x, we have f of negative x equals negative f of x. So putting a negative in front of the x, it's the same thing as if I had put a negative in front of the entire function. And just note that no function can be both even and odd, with the caveat of the constant function f of x equals 0, since 0 is not even, well, positive or negative, essentially. So no function is both even or odd, but functions can be neither even nor odd. Okay. Let's see an example. Oh, actually, summary first. So to determine if something's even or odd, since it can't be both, all you have to do is see, well, if let's find f of negative x, and then check if you got back the same answer. If so, it's even and you're done. Next, find negative f of x and simplify it. And then check, does f of negative x from part 1 equal negative f of x? So notice in the first part, we put a negative in front of the x. And in the second part, we put a negative in front of the entire function. So you check if those two are the same. If neither of those things are true, then it's neither even nor odd. Here's our example. So let's check if something's even, odd, or neither. So starting off, we always want to find f of negative x. F of negative x is 5 times negative x to the 7 minus 6 times negative x to the 3rd. And that 7 should have been outside the parentheses. There we go. Minus 2 times negative x. So this negative x to the 7, well, 7 is odd, is a number, is odd, which means that I'm still going to have a negative out front. So I have a negative 5x to the 7, right? Because if the 7 in the exponent were an even exponent, we know our negative would have squared away, because negative times a negative is a positive. But when we have an odd exponent, that negative is not going away, so it stays in the front. Same thing happens in the next term. I have a minus 6, then I have a minus x to the 3rd. That minus is not going away by the exponent of 3. If it were a 2, maybe it would have squared away. Actually, would have squared away. But this one's a 3. It's an odd exponent. Therefore, we're stuck with this negative in the front, which means we have a negative from the 6 and a negative in front of the x, which is not going away with the cube. And so that becomes a plus 6x cubed. Now, similarly, we have a negative 2 times negative x. That's a plus 2x. So essentially, when you have an odd exponent and you're raising a negative to an odd exponent, that negative's not going away. So it might combine with another negative like we had here, but it is not going away in general. If it's an even exponent, it is going away. So now we need to think, does this equal our original function? And no, that's not true, right? I have a negative 5x to the 7 versus a positive 5x to the 7 just to start. Those are clearly not the same function. So it is not even. So now we want to look at, well, what is negative f of x? Now my negative's in the front, which means now I'm looking at negative, and then I write in f of x. 5x to the 7 minus 6x cubed minus 2x. And if I distribute this negative, I have a minus 5x to the 7 plus 6x cubed plus 2x. But this also does not equal f of x. So now we're going to compare if f of negative x equals negative f of x, right? So does this one equal this one? And yes, that is true. That is true, because we do have, in the simplified version of negative f of x, we have a negative 5x to the 7 plus 6x cubed plus 2x. That should have been a cube. So therefore, it is odd. That is true. Now, moving on to section 2.5. We are going to be talking about transformations of functions, and it's all going to come down to some of these core functions written here. Essentially, we take one of these functions written here, one of our core functions, and we either move it up, down, left, or right, and we stretch it or shrink it. And so we want to get used to identifying what do each of these standard functions look like, and how can we change them to look like new functions. So we have the identity function y equals x, which is a straight line. We have y equals x squared, which is our standard parabola. Y equals the square root of x, which is our typical square root function coming out from the origin. Y equals x cubed, this lovely curvy one. We have y equals the cube root of x, which is x cubed kind of turned on its side. We have the reciprocal function, and we have the absolute value function, which is our big old V. So these are all functions you're going to want to be able to recognize and then think about, okay, what if I add a little bit or subtract a little bit? What happens? That's what we'll be going through next. So we're going to take the core functions and consider them our building blocks. Then we can either shift horizontally or vertically, and then we can stretch or shrink. We can also reflect them across an axis. All of these new functions are what we call transformations. So for a vertical translation, if we have some positive b value, we take our function f and we add b, that's the same thing as if we had shifted up b units. So if we take some core function that looks like this, and we shift it up by 5 units by adding 5 to it, the new graph will look exactly the same as the old graph, just moved up 5 blocks on the graph. Similarly, if b is negative and we're subtracting b, then we've shifted down b units. And so this one, vertical translations, they move in the natural direction. If I add 5, I move up. If I subtract 5, I move down. We can also have horizontal translations. So if I have some d value and I want to move it left or right, well, I can take my function and I can subtract d from x, and that's going to move me to the right, okay? Now, if I take my function, I add d to my x value, so notice that's inside the parentheses, I'm actually shifting to the left. So as I take our example function here, and I take my x value inside the raised to the 4, and I replace it by adding 7 values to it, that actually moves the graph to the left. So as I add values to x, I shift the graph to the left. So it's kind of a strange opposite. You would expect to add 7 units to shift us to the right in the positive direction. But because it's inside the parentheses, it actually moves it in the opposite direction. So vertical shifts go in the natural direction, but horizontal shifts kind of go in the opposite direction from what you'd expect them to do. So you just have to kind of memorize that and get used to working with it. But when I add values, I move to the left. If I subtract values from x, I move to the right. Now I can also reflect things across the x and y axis. For example, I could take, I'll try it over here, something like y equals x squared. And I could reflect it over the x-axis to make it look like this, right? I could just flip it. So if I took a mirror image over the x-axis and flip it down, and to do that, all I have to do is put a negative in front of the entire function. So this one is y equals negative x squared. Now, I can do the same thing with the y-axis, where I want to flip a graph over the y-axis, And all I have to do is put a negative in front of the x, but that has to be inside the parentheses. So now let's describe what's happening to each of these graphs. So for part A, we have f of x equals x squared minus 6. So clearly x squared is our core graph, and we're subtracting 6 from it. And that means that we are going to be shifting down 6 units because we subtracted 6. Now for this one, our core function is these absolute value bars. And notice this minus 4 is actually inside the absolute value bars, kind of inside the function. So this one is actually a horizontal shift. So we're shifting left or right. And because we're subtracting 4, we're actually moving to the right 4 units. Now subtracting 4 makes you want to move it to the left because you think it should move in the negative direction. But that's not true here. We're subtracting 4, so we're moving to the right 4 units. Now we have, for part C, h of x is the square root of x plus 2. Well, that again has a plus 2, but it's inside of the square root. So it's a horizontal shift. We know we're shifting left or right. Because we're adding 2, we're actually shifting to the left. Left 2 units. All right, now let's see what happens here. Now we have the square root of x plus 2 and then a minus 3. So we still have the same idea under the square root where we're adding 2. So we are still shifting left 2 units. Only now we're subtracting 3, so we're also going down 3 units. We did both. One of them is inside the square root with the x, and that's our horizontal shift. And one of them is outside the square root, which is the minus 3, and that's our vertical shift. Now for this last one, we've stuck a negative in front of the x squared. And so that's a negative in front of the entire core function. So that is a reflection with respect to the x-axis. All right. Now let's suppose we have something like this, where we're given a point negative 11, 4 on the graph of y equals f of x. And we want to think about a corresponding point on the graph y equals g of x, where g of x is 1/2 of f of x. Well, if we take 11, 4, that is an x f of x point, right? This is my x value. This is my f of x value. And here, for this graph, we want to be thinking about x g of x points. And we know that g of x is 1/2 f of x. That's what's given here. Okay, so if I know that essentially f of 11 is 4 here, so this tells me f of negative 11 equals 4. And now I want to know the corresponding point. So essentially I want to know negative 11 comma whatever g of negative 11 is. That's what it's asking me for. Okay, but now I know negative 11. Well, I know, let's take back a step. I know g of x is 1/2 f of x. So g of negative 11 is 1/2 of f of negative 11, right? 1/2 of f of x. Okay, so that's 1/2 times, well, f of negative 11 is 4, so 1/2 times 4, which is just 2. So we know that the corresponding point is negative 11, comma 2. So essentially all we had to do was look here and say, oh, g of x corresponds to 1/2 f of x. So we just got to take that y value on f of x and multiply it by 1/2 to get our new point. This is the corresponding point that it was looking for. Another type of question you might be asked is to write an equation for a function, and you're given the function, and then you're asked to shift it left 3 units and up 2 units. So we know this one is a horizontal shift. The left 3 units, that's a horizontal shift, which means it needs to go inside parentheses. And we know if we want to go left 3 units, we actually need to add 3. Then if we want to go up 2 units, well, that's a vertical shift. So we just want to add 2, but that's not going to be inside the parentheses. That'll be outside parentheses. So what that ends up looking like is I have 3 times x plus 3. Here's where I get the plus 3 involved. It's inside parentheses, and that's what gets squared. So essentially everywhere I see an x, I replace it with an x plus 3 is what we're doing. So now I have a plus 6 times x plus 3, right? Again, replace the x with an x plus 3. That's how we shift it to the left. And then we just have to add 2 in order to shift it up 2 units overall. And this is our new function. And you can leave it like this in Pearson this week. But that's it. You see that inside parentheses, we have a plus 3, and overall, we have a plus 2. Now, we can also stretch and shrink our graphs. So if we want to vertically stretch and shrink our graphs, to vertically stretch, well, let's look at the function for a second. So to vertically do either stretching or shrinking, we multiply the function by some a value in the front. And if that a value, an absolute value, is greater than 1, we're actually stretching. But if it's less than 1, it's essentially some fraction less than 1, we're actually shrinking it. And anytime a is actually negative, we're actually flipping it across the x-axis like we saw before. That would be like sticking a negative out front here, which we know means we're reflecting across the x-axis. So that's what we want to look for these kinds of problems. So here's a few examples. Let's look at the first one. Our core function is y equals x cubed minus x. I wouldn't say core function, our kind of starting function here is x cubed minus x. And the a value we're taking is 1 over 10. So it's being multiplied in front of the entire function. Well, that 1 over 10, that's clearly between 0 and 1. So this is a vertical shrink. And you can tell that we went from a very kind of bumpy function here to a very almost leveled out function here. There's not so much change in the y direction going on with this new function. So therefore we shrunk it vertically to kind of flatten it out. Whereas now if we look at the same base function and instead we multiply it by a 2. So here we have an a value that is 2 and it's positive and it's greater than 1. That means we're actually stretching it vertically. So we go from this black function here to then having a little bit more height and a little bit more low in the new function. We've stretched it vertically. That's what multiplying by 2 does. Now we could do that as well as then multiplying by a negative. So instead of positive 2, we could have negative 2, which gives us the same vertical stretch that we had before. But now instead of going up in the second quadrant and down in the fourth, we're going down in that third quadrant and up in the first. So it kind of just flips it over the x-axis, right? It's flipping it along this line here. So that's what happens when we have a negative. If you have a negative value, it just flips everything, and then you can also have the stretch or shrink with the negative. But that's what it looks like when we multiply a function by a number out in the very front. Now, instead of putting the number out front, we could put the number right in front of the x, which, just like before, when it's inside the parentheses, now we have a horizontal stretch or shrink. And this, again, with horizontals, goes in the opposite direction than what you would expect. So if I have a C value greater than 1, I'm actually shrinking horizontally, actually pulling things closer together. But if I have a C value that's actually a fraction between 0 and 1, I'm actually stretching horizontally, and the graph will kind of pull out to the edges a little bit more. And anytime your C is negative, you've actually flipped it across the y-axis. Let's see those examples now. So our base function is still x cubed minus x. And when we put a 2 in front of the x inside the parentheses, we actually get a shrinking. You can see the black graph kind of turn into that red graph by squeezing it together. Alternatively, if we'd stuck a 1/2 in front of the x, then we would have seen a stretching. So you can see how the black graph kind of stretched outwards here horizontally. And then similarly to before, if we stick a negative out front with our C value here, we actually get a flip over the y-axis and a stretch. You need two things at once. So now let's describe what happens to each of these graphs. So for this first one, I have a 2 out front. It's not in the some parentheses with the x, it's just out in the front. So this is an a value, it's an a equals 2. And when I have a equals 2, it's greater than 1, so it's a vertical stretch. Now for the next one, I have a 1/2 out in front of the absolute value bar, so that's again an a value, which is 1/2. And 1/2 is less than 1, so this is a vertical shrink. For this next one, my 2 is in the parentheses with an x. That all of it is being cubed, so this is a C value equal to 2. And because it's a C value, it's a horizontal. And it's actually a shrink. Because my C value is greater than 1. So in this case, if my C value has gone up, the function has actually come together. It's the opposite of what we want it to be. Now lastly, I have a square root function, and my 1/2 is in the square root with the x. Therefore, I'm looking at a C value of 1/2, and it is a horizontal stretch. Now we can look at what happens if we actually don't have a function f. We don't have an actual equation here. So when that happens, and you're looking at a graph of f, and on your homework, you're asked to identify which graph represents -5f. What I want you to do is pick one of these points. So right here we have 0, 1, right? And you want to look at what happened to that point. If I want to get this to look like -5f of x, then my y value is going to be multiplied by -5. So my new point is going to be 0, -5. Then you go and you look at your graph options. Here we just have the 1. And you see that the graph now hits the point 0, -5. That's how you can tell that this is your graph you're looking for. Let's do it again. Let's say with this point over here, we have 1, 2, 3, 4, comma, -1. That means on a corresponding graph, we should have 4 and then -1 times the -5 gives us a +5. So 4, comma 5 is 1, 2, 3, 4, and up 1, 2, 3, 4, 5. Here's 4, comma 5. And it does match up with the original. We're multiplying the original by -5. So we don't always need a function. We can just look at certain points, look at what happens to their y values if I multiply it by a number. Now to wrap it all up, your textbook has this great chart on page 137 that gives a full summary of your transformations. So we either have vertical, horizontal, we have our reflections, our vertical shrinking, and our horizontal shrinking. So if this is a little bit small for you, I don't blame you. You can check your textbook, which is linked through the Pearson website. And you can go to this page and get a really nice screenshot of it there. This is going to be helpful to memorize, maybe in some flashcards and that kind of thing. For the exam, you'll have to get used to working with these. So as always, please reach out if you have any questions. Thanks, guys.